I'm Steve Strogatz.
And I'm Janna Levin.
And this is The Joy of Why, a podcast from Quanta Magazine exploring some of the biggest unanswered questions in math and science today. Here we are. Hey, Janna.
Hey, Steve.
I've got something really fun queued up for you today.
Good. I'm looking forward to hearing about it.
Okay. Now, I think this should be kind of in your wheelhouse. It's about gravity.
That's definitely within my wheelhouse.
And now let me add one more word, quantum gravity.
Yeah, and now it's in no one's wheelhouse.
That's interesting, isn't it? Because it's such a hard, open problem in physics. So I had the chance to speak to a great young physicist named Monika Schleier-Smith. She's at Stanford. And she is taking an approach I've never heard of anywhere else, which is to try to build a kind of toy model of quantum gravity in the laboratory.
Wow.
Funny thing, right? I mean, you think of quantum gravity as purely theoretical pencil and paper stuff.
Yeah, absolutely. That seems maximally hard.
Maximally hard, right? Do you ever hear this idea that gravity might emerge from entanglement?
Oh, yes. It's one of my favorites.
Is it?
Actually, yeah. I find it really intriguing. I kind of think of it as the entanglement as like threads at the quantum level, and it embroiders a world that from afar looks like it's smooth and continuous, and you look up close and you realize it's really these entangled threads.
Very poetic. I like it. Well, that is sort of the spirit of what we're doing in this episode with Monika. She's going to talk to us about the ways that she tries to entangle thousands of atoms that she has maintained at very low temperature so that they can express their quantum mechanical nature and get entangled. But it's many-body quantum entanglement.
So they're all
we're talking
entangled
about.
with each other as opposed to just pairs?
Right. That's the new wrinkle here. I'm only used to the idea of, you hear a lot about entangling two atoms or something like that in the old, like Einstein, Podolsky, Rosen thought experiment, and then later recreations of that in the lab. This is many-body entanglement, thousands of atoms. And I think she's trying to stitch together some kind of fabric of space and time like you just described.
Wow. I mean, I'm not sure how she would get gravity out of that quite yet, but that's fascinating. I mean, I always thought there was a kind of monogamy of entanglement. So if one particle was maximally entangled with another, it had to be monogamous. It could not also be entangled with a third partner.
Well, that's interesting. I've never heard that idea.
So maybe each one's partially entangled with another, right? So they're not maximally entangled one-to-one.
Yeah.
It's a kind of polyamory of entanglement.
Well, I knew you would get interested in this, and so I think we should just hear from Stanford physicist Monika Schleier-Smith. Hey, Monika, welcome to the show.
Thank you.
Before we get rolling on the question of what you've been doing in quantum physics experiments, I read somewhere that you got an early start, even as a high school student, doing nanotechnology in a lab.
So, I was very fortunate as a high school student to get to do summer research internships at a company called the MITRE Corporation. I wasn't yet working in the lab, but I was getting to really grapple with forefront issues of cutting-edge research in nanotechnology. And that was really remarkable, being a 16-year-old getting to read scientific papers and be in a research group.
Amazing. When you say you weren't in the lab, did they have you doing computer simulations or what kind of thing?
That's right. I was doing computer simulations. I was developing some ideas that actually led to a patent. We were able to collaborate with a group at Penn State that had the expertise and was able to take it to the next level and led to actually publishable results. And after I left, they actually started a lab based on some of the ideas we'd been brainstorming about when I was there.
What a great start to a scientific life. Should we picture you as a little kid with scientific parents or going out in the woods looking at bugs, or what was your deep background?
Definitely going out into the woods, exploring. My mother, actually, her background was in linguistics and really more in the humanities, but she always wished she had gone into science. And so that was a very strong influence. And I have an older brother who took the first steps in studying physics in college, and I guess I was inspired and followed in those footsteps.
Quite a family. Well, you're part of this giant enterprise of modern physics. And there's the so-called standard model. I mean, it's a super successful theory, but even the most ardent proponents of the standard model would agree there are a few things that have to be filled in Can you tell us a little about what is that model?
Yeah. So the Standard Model describes a wide range of particles that make up matter in our universe: electrons, protons, and their constituent quarks, photons. And part of the Standard Model, for example, is also that some of these particles are responsible for electric forces between charged particles, electrons and protons. There are additional particles that are responsible actually for mediating those forces. A photon is actually responsible for mediating these electric forces, kind of bouncing between the charged particles that are interacting. One thing that's missing actually in the Standard Model, one significant omission, is a particle that mediates the force of gravity. Right? So in the same way that charged particles can attract or repel depending on their charges, gravity seems, on the face of it, very analogous. The mass of an object is kind of the equivalent to the charge. In the case of electric forces, the mass determines how strong the attractive force is in gravity. But the Standard Model doesn't have that equivalent of the photon for electromagnetism. It doesn't have something like a graviton that would mediate the gravitational forces. It's possible to have this theory, the Standard Model, that is extraordinarily well tested, but has this sort of glaring omission of gravity.
Right. So you've mentioned it doesn't have the counterpart of the photon, the graviton. I mean, we talk about gravitons, but they're not part of the Standard Model. I hear there are a few other things like neutrinos, these tiny neutral particles, shouldn't have any mass, but they do.
Yeah, and there are big mysteries in our universe also about what we call dark matter and dark energy. 70% of the energy that should be there is missing and is in the form of this dark energy that we can't account for. So lots of big mysteries in the universe, even though the Standard Model is experimentally extraordinarily well tested.
Okay, but you put your finger specifically on this missing part of gravity in the Standard Model, and so that's what we'll be talking about mostly. So given that gravity is not in the Standard Model, even though we know it's a real important force, it's keeping us both in our seats at the moment, how is that hurting our current understanding of the universe? We do have a very excellent theory of gravity. Newton's theory, or then if we want to get fancier, Einstein's general relativity.
That's right. We do have an excellent theory. Einstein's general relativity is also extraordinarily well tested. If I go back to the analogy with electromagnetism, the sort of classical picture is that electromagnetic forces, they're mediated by electromagnetic waves or light. And in gravity, we've by now even detected gravitational waves, right? So in its own right, gravity is also very well understood and tested. And at some level, the challenge is that the microscopic description is really kind of quantum mechanical. Quantum mechanics is a great theory for describing systems at very small scales. But gravity is a theory that works very well in the regime of massive objects, the motion of planets. And these are tested in very different regimes. It's hard to get into a regime where actually both gravity and quantum mechanics matter. It's mostly so far in thought experiments that we realize we don't have a unified theory and that there's something missing when we can't connect the rules of quantum mechanics with the rules of gravity.
That's interesting, this last point that you just raised, because there are parts of relativity that play nicely with quantum theory, right? Like we do have special relativity.
That's right. And again, I think it's partly this issue that one theory or the other applies well, or one can put in the minimal ingredients, let's say special relativity of gravity, and combine that with quantum mechanics, but somehow a full unified theory is still missing. I mean, just to give one other example that I find kind of puzzling, in gravity, space and time are treated on an equal footing. In quantum mechanics, we actually don't treat them on an equal footing. Systems evolve in time, and space is thought of completely separately. And so somehow there are these two inconsistent ways of thinking about the universe. And one has to start doing thought experiments about things like what happens to information that falls into a black hole to start to realize that actually, to really fully understand our universe, we need to reconcile them.
I'm glad you put your finger on space and time, because that's really what we do want to be talking about here. I mean, they're all linked up, aren't they? Space, time, gravity, and then this other whole story of quantum mechanics. So let's talk about the possibility that space and time might not be as fundamental as we used to think.
Yeah, and so one of the remarkable ideas that's emerged from theorists who think hard about this problem of reconciling quantum mechanics and gravity is the notion that perhaps The fundamental building blocks of gravity really are quantum mechanical. A number of years ago, I found a quote from, you might say, the father of the atom, Democritus, right? He was the Greek philosopher who recognized that matter is not just some smooth, continuous thing. It has actually fundamental building blocks that are atoms and molecules. And then he made this point that phenomena such as, hot and cold, sweet or bitter, taste, temperature, colors, emerge from the microscopic configurations of individual atoms or molecules. I don't need to think about the positions of all the individual atoms to look at an object and say it's red, right? And so color is this kind of emergent phenomenon. So the question that has been explored in recent years in this effort to unify quantum mechanics and gravity is, could it be that gravity is actually also an emergent phenomenon? So the microscopic constituents are really quantum mechanical, and gravity emerges as this sort of simplified, smooth description of what fundamentally is really some complex interacting quantum system. And I find that idea fascinating. And how might gravity emerge from quantum mechanics? The connection that's conjectured is a phenomenon called entanglement.
Go on. I want to hear more because it is incredibly fascinating. The first time I heard it, my mind was blown. Tell us.
Yeah. So entanglement is the idea that I can store information, not just in individual bits or particles, but actually in correlations. So, in your computer, you have information that's stored in bits that are in like a 1 state or a 0 state, but that information it's really stored locally in an individual bit. So the quantum analog of a bit, we call it a qubit. And it's possible to have information that's not just stored in a single qubit. If you look at the state of a single qubit, it looks completely random. In fact, randomness is an inherent aspect of quantum mechanics. But if you look at the states of 2 of these qubits, you would find they're always either both 1 or they're always both 0, even though each one individually looks random. And so there is actually some order in the randomness, some information that can be stored in a way that you can only access if you look at both of these qubits. So this idea of correlations and information that are sort of hidden in this randomness, that's this notion of entanglement. And one of the sort of challenges this brings up is that describing a quantum system is actually much more complex than describing the bits in your classical computer, because you need to keep track not just of the states of the individual qubits, but of all of these correlations between them. So sometimes I like to sort of visualize a graph where I have my row of these qubits, but then I want to sort of draw some lines that indicate something about the structure of which ones are correlated with which ones. And that's still an overly simplified description. But roughly speaking, these correlations I can visualize as some connections between the qubits. And now the idea is that perhaps actually this notion of gravity being an emergent phenomenon, the idea is actually describing those correlations. And I kind of think of it as there's this one additional dimension that allows me to capture extra information that describes the structure of correlations. There's some mapping from the quantum mechanical system to actually a geometrical description in which the distance between the qubits says something about how strongly they're correlated. This notion has also been given the name of holographic duality. So why holographic? A hologram is something that has 2 dimensions, but actually it looks like a 3-dimensional image, right? It has this sort of additional dimension. So there's this notion that somehow once one accounts for the entanglement between all these degrees of freedom, gravity may emerge as a description of those microscopic quantum building blocks, a sort of smooth macroscopic description in terms of space-time curvature and geometry.
Okay, so that is a lot going on there.
Yeah.
And that's fine because you've given us a lot to chew on now. You said this really deep, interesting thing that, if I can paraphrase it and correct me if I'm not hearing you right, it's sort of like saying distance is an illusion. What really is meaningful is correlation, right? That's sort of the idea that things that look like they're a certain distance apart, that's our macroscopic way as big creatures of thinking about what microscopically is about strong correlations or maybe weak correlations.
Yeah, exactly. Like a long distance would sort of correspond to a weaker correlation, roughly speaking. Exactly.
Okay. So we'll have to come back to that, this idea that space and distance is really just an emergent way of talking about what's really going on under the hood, which is correlations. of different strengths. But so you spoke about that there can be information in the relationship between two things that are otherwise completely random on their own.
Right. I kind of like to use the analogy of a coin toss, right? And so like imagine I'm here and I'm tossing coins, and every time I toss one, you'll also toss a coin. And when we look at the outcomes of those coin tosses, I'll see something completely random. You'll see a random sequence of heads and tails. And classically, that's all there is to it, and there's no correlation. But quantum mechanically, we could have a situation where every time I get heads, you get tails. And every time I get tails, you get heads, despite the fact that I'm here in California and you're
in Ithaca.
Yeah, exactly. And so that would be very weird, right?
Right, especially where I'm far enough away that you couldn't possibly get a signal to me fast enough to influence me.
Exactly. There were more and more experiments over the past 20 years or so trying to really make sure that we verified entanglement in a setting where these two measurements were far enough apart that there couldn't be any information traveling between them and things like that.
Okay. So as it started, it was a very theoretical idea going back to the 1930s or something, right? From Einstein and Podolsky and Rosen and Schrodinger and people like that. But now fast forwarding to almost a century later, it's not obvious to me how you would maintain the entanglement over great distances. Does it take tremendous care to keep them entangled?
It's tremendously challenging, and to bridge long distances, there are different choices you could make of photons because they travel at the speed of light across long distances. But even so, there's some possibility that the photon, if it's sent through an optical fiber, that it's lost along the way, or also if it's sent through free space, there's still some chance it'll get absorbed along the way. Sometimes there are tricks where you can do what's called heralding, that like maybe you don't succeed every time, but there's a way to know actually whether you successfully created an entangled state.
Okay. But now it sounds like you and your students are doing this every day now. So maybe you should tell us, what are you entangling?
In my lab, we work on smaller length scales. The particles that we entangle are atoms. And an atom is an angstrom scale object. Ordinarily, you would think that if I have two atoms that are, let's say, a millimeter apart, they won't interact, they won't become correlated. But that's actually a length scale where we are able to generate entanglement. And the way that we do it is, in fact, actually using light. I use this notion of mediating interactions. We use a very engineered setup in the lab where a photon can bounce between two atoms or between two clouds of atoms and introduce correlations and entanglement between them. And that's not the only way that one can generate entanglement among atoms. I'll focus on this one because one of the nice things about photons is they can quickly bridge long distances, and they can give a lot of flexibility. Naively, you would think what will naturally happen is atoms will maybe bump into other atoms that are near them, and you'll sort of generate strong correlations between neighboring atoms. And what we like to be able to do is have some network where we can actually control the structure of correlations and decide by some knobs in the experiment the atoms that are most strongly correlated. That's a way of using photons to program the graph of correlations in our case, an array of clouds of atoms.
So I do want to hear about the clouds of atoms and the programmable networks that you're building or engineering. But can you give us an oral picture? Like if we were standing behind you, looking over your shoulder, what would we see?
In any given lab, in my research group, you would see something like 2 to 3 optical tables. So each of these is something like 4 foot by 8 foot, maybe even a bit bigger. There's usually one table that has a bunch of lasers, because I mentioned we need laser light as our tool for manipulating atoms. So you'd see these lasers, you would see lots and lots of mirrors and various other optical elements to steer the lasers into the right places. And then all of these laser beams get steered into optical fibers, going from one table to another table, which carry that light to where our science experiments actually happen. And that second table has on it an ultra-high vacuum chamber, which we need in order to have particular atoms in one of our labs, it's rubidium atoms, that are sort of well isolated from anything else in the lab, right? So we want to be operating in an ultra-high vacuum environment where I can just create a cloud or a few clouds of atoms that are at very low temperature and that are essentially suspended by laser beams in the middle of this vacuum chamber.
These rubidium atoms are in what you're calling high vacuum. So meaning they're not bumping into any oxygen or nitrogen. There's no air in there.
Right, yeah.
They're just rubidium atoms, which I don't even really know how to think about rubidium. I've heard of rubidium.
If you remember your periodic table.
Yeah, no, I don't. Tell me.
I'll just say it's in the first column. And what that means is basically there's one valence electron, so one outer electron that is relatively well isolated from all of the other electrons. And that actually turns out to be convenient for making it a relatively simple atom to control and manipulate with lasers.
I see. And why do you want to have a cloud of them?
So I'll say that I might actually prefer not to have a cloud, but we work with a cloud. For the class of experiments I described where we use light, photons, as our means of generating some network of interactions between atoms, we can actually generate stronger interactions if we use many atoms rather than just one. If I go back to sort of the wave picture of light, there's constructive interference, a photon bouncing off one atom and hitting another atom to make them interact. If I have many atoms, the waves that they scatter can interfere constructively, and that can actually enhance the strength of interaction.
Cool.
And so at least for kind of first experiments, it's been convenient for us to work with, let's say, clouds where each cloud has 1,000 atoms, and then we have an array of such clouds. But there is a path that we're interested in actually going towards single atoms where each atom interacts more strongly.
Okay. But so for now, we could think of a cloud of 10,000 atoms or something. But you mentioned low temperature. So you want to tell us how low?
Yeah. So typically we work with temperatures that are on the scale of tens of microkelvin. 1,000th of a degree above absolute zero would be a millikelvin. We're often a factor of 20 or 50 below that in temperature.
Wow.
And so that sounds extraordinarily cold. One thing to keep in mind is actually the room isn't cold. That vacuum chamber isn't cold. If you touch it, it's at room temperature. But it's just this cloud of atoms suspended by laser light that we are able to actually bring to very low temperature using tricks of laser cooling.
There's some way of using the lasers to hit the atoms in just the right way that sort of knocks the wind out of them.
Exactly. That's a great analogy.
Okay, I see. So I'm getting the picture now. You've got these clouds, 10,000 atoms. You get them very cold, not to the point where they're a single quantum object in the sense of Bose-Einstein condensate, but still, they're constructively interfering in the wave picture enough that it's sort of like a strong edge in this network of interactions that you're trying to build.
And maybe I can also just add the reason we don't need to get them down to this state of matter of Bose-Einstein condensation. It turns out if the atoms are moving around a little bit, that's okay for the experiments that we do. There's still a sense in which we place all of our atoms in a given cloud into the same quantum state. So they're not all at the same position, but what we care about most in our experiments is some internal state of the atom. So there's that electron we talked about, and we control which state that electron is in. We control which way its spin is pointing. And so we have actually very good control over the internal states of these atoms, and those will all be identical in a given cloud.
So is the entanglement that you're trying to set up at the level of spins then? Because I mean, I know in the traditional old thought experiments about entanglement, they used to frequently talk about the spin of two different particles.
Exactly. And so the spin is sort of the real physical implementation of what I talked about before with the heads and tails of the coin, right? These two possible states of the coin are like a spin that points up or down. And actually in quantum mechanics, a spin could point anywhere in 3 dimensions. But when we decide to do a measurement, we have to choose what we call a basis. We can measure, does it point up or down? Does it point right or left? But we actually can't determine both of those things at the same time. So these are examples of incompatible observables. A famous example is position and momentum of a particle. 2 different components of the spin, the vertical or the horizontal, that would be another example.
Okay, so now we've got the visual of you in your lab and the optical table and all the lasers and mirrors and cables. But then now that you have this ability to entangle these clouds, you can make whatever networks you want, if I'm hearing you right. You know, you're doing this very fundamental research about what in the jargon might be called something like many-body entanglement. So that's sure to be important.
Right. So having control over entanglement can be a resource for making better precision measurements when what limits you is quantum uncertainty, the sort of randomness inherent in quantum mechanics, or another one, quantum computation. The idea is if you have a sufficiently well-controlled quantum system where you can really program in the interactions in the same way that you program your classical computer, but now the building blocks are quantum bits, then one place that seems very natural to give us an advantage is precisely in describing quantum mechanical systems, be it the behavior of electrons and materials, or be it actually problems from chemistry, for example.
I'm kind of dumbfounded a little bit. I mean, you have these many body systems. She somehow managed to entangle them in this kind of a network. How do I get from there to gravity? Why would I think it's gravity and not some other complex system that emerges from the many body problem?
That's really a good question. I think she is looking for signatures of something that would be like a discrete analog of curvature of a continuous space. So networks can have properties like curvature the way that smooth manifolds can have curvature.
Wow. Amazing. So she's trying to make a space-time or like a manifold or something.
It's something like you said with your beautiful analogy of the embroidered fabric, that it might look like a nice smooth dress, but you look up close, it's a lot of threads stitched together.
Right. Oh, fascinating. So the network itself is an emerging space-time in some sense.
Something like that. But it's controversial what she's doing. And as she says, it's also possible that this won't lead to a deeper understanding of gravity, but maybe it will help with precision measurements, or maybe it will help with quantum computing. We're going to get right into that. We're speaking with Stanford physicist Monika Schleier-Smith, who's been telling us about her toy model of gravity. So there is a certain amount of controversy attached to this idea that gravity and space-time emerge from quantum entanglement. We haven't really said that out loud, but maybe we should.
Right, absolutely.
So even if that doesn't pan out, you're not wasting your time, I think, in the lab.
I like to think not. Again, it's not the only thing I'm working on, but also for me, I'm fascinated by the idea that gravity in our universe might be an emergent phenomenon, where the building blocks are quantum mechanics. But there's also another way to think about this whole field, which is to say there are certain cases where one sees this so-called duality. So there's a strongly interacting quantum system that has an equivalent description in terms of equations that look like gravity. And whether or not gravity in our universe is a manifestation of quantum mechanics, these theoretical tools of taking a strongly interacting quantum mechanical system and mapping them to a description in terms of curved space and gravity, maybe that gives you new ways of calculating things about the quantum mechanical system or new insights into how it will behave.
Okay, I'm sold. This is good. So maybe you should tell me then about this kind of toy model of gravity. What do these networks have to do with quantum gravity and space-time?
Yeah. This effort at understanding quantum gravity has been almost purely the domain of theory until recently. And so my thought was, if gravity might be an emergent phenomenon, if curved space might be something that can emerge as a natural description of quantum correlations, can we build a system where we start to see this phenomenon of something that looks like curved space emerging as a description of the quantum correlations? Before we did an experiment, rather serendipitously, we began talking with a theorist at Princeton named Steve Gubser, who actually tragically passed away in a climbing accident a few years ago. Yeah. But Steve was working on this effort to reconcile quantum mechanics and gravity. He had developed, I would say, a particular version of this holographic duality, right? So holographic duality was this notion that I have a quantum mechanical system that I can think of as kind of living on the boundary where the higher dimensional space has gravity, and the gravity gives rise to curvature in that space, and the distances within that higher dimensional space say something about correlations in the quantum system on the boundary. What was really valuable to us about talking to Steve Gubser was that he was working on a formulation of this holographic duality where there's a very nice way of actually visualizing bulk geometry. He wanted actually a discretized theory. So what do I mean by that? He wanted there to be a shortest length scale in his theory, motivated actually by the fact that in our universe, there's a length scale called the Planck length, where you expect to start running into major problems in reconciling quantum mechanics and gravity. And anyway, so Steve had this discretized version of holographic duality, where the bulk geometry is represented by a tree, and the boundary where the quantum mechanical system lives, it lives on the leaves of the tree.
Ah, nice.
Yeah, so you can kind of imagine if you're at the trunk of the tree, that's somewhere in the middle of the bulk, somewhere in the middle of the part that's described by gravity. And then that trunk has two branches, and each of those has two more branches, and each of those has two more branches. In just a few steps, the number of leaves actually grows exponentially with the distance that you go out from the trunk. If you think of the tree as kind of radiating outwards so that the leaves end up on a circle, you have this weird thing where the circumference of that circle is actually exponentially larger than the distance measured in how many times you need to branch to get to the leaf. So we have this graph, and again, I kind of think of it as I can visualize it as the leaves live on the circumference of a circle. The circumference is exponentially larger than the diameter instead of being larger by a factor of pi. And so somehow this isn't just a flat disk, it's curved, and it actually has negative curvature.
Oh, I see. You're saying that's why it's curved, because if it were just a flat disk, it should only be the 2 pi times the radius. But this is way more circumference than that.
Exactly. If anyone in the audience has seen some prints by Escher, so he'll tile a disk with fish. And in the middle, there are big fish, and around the circumference, there are lots of really tiny fish. And that actually really is a representation of this hyperbolic geometry.
Yeah, and why hyperbolic? I mean, there's also this nice picture of, if you're trying to flatten out a rug, it may be fine. But if you try to flatten out a piece of lettuce or something that looks like a saddle,
right, yeah,
it keeps popping up, right? You can't flatten it out easily, and it's because it has too much circumference for its distance from the center. So that's what negative curved space is kind of like.
Exactly. And so this tree graph is a discretized version of this negatively curved space, or what is called anti-de Sitter space in the context of general relativity and gravity. So we kind of asked ourselves, is there a quantum mechanical system we can build that would have correlations that make it sort of look like it lives on the leaves of a tree graph? And we realized there's a toy model where a given site in my array can talk to its nearest neighbor, its second neighbor, its fourth neighbor, its eighth neighbor. It's not a lot of connections that you need to build, but they give you an efficient way of getting information from one point to any other. So we've actually been thinking about that. And then we got in touch with Steve Gubser, and he pointed out, if you tweak this model just a little bit, so that the longest range interactions are the strongest, like the atoms that are far apart physically actually have the strongest interactions, that might make it look like your system of atoms lives on the leaves of a tree graph.
Mm-hmm. And so what would you have to measure to see a signature that the counterpart of space is being curved?
Essentially, we measure spin correlations. If a given spin is pointing to the right, how likely is it that another site of our array also has the spin pointing to the right? So my students started thinking about what's a clever way to plot these data. You have to put some constraints on how you plot it. It's nice to plot things on a page, so in 2 dimensions. And so he ended up with some plot where the sites ended up arranged around a circle. The ones where we measured the strongest correlations were close to each other. And the order of the sites is actually very different from what it is in our physical system, but it's a nice way of representing things as near each other if the correlations between them are strong. And then he also started drawing lines. So pairs of sites with the strongest correlations, he drew a line between them. And then he sort of treated those as a new, bigger site, asked what's the average direction the spin is pointing on that bigger site. And by iterating that process, the picture that popped out was precisely this tree graph.
Let me make sure I understand one aspect, though. Since you have so much ability to program who's interacting with who, what part of the results is a surprise to you? How much is built in and how much is not built in?
Yeah. So at some level, when we did the experiment, we did know what we thought should come out.
Right.
We didn't know yet how we would analyze the data. And this way of actually visualizing the tree graph came up in discussions between me and my students, and that wasn't something we had thought about before we did the experiment. In general, we often start with something where we know what should happen. And the goal is eventually, and we're not there yet, to be honest, but the goal is eventually to get somewhere where we actually don't know what will happen. There are some proposals for more kind of agnostic methods of trying to go from a quantum mechanical system to determine, does it have an emergent description in terms of some curved higher dimensional space. What is the geometry? What is the metric on that higher dimensional space? So I think that's an important direction for future research, is to go beyond just we build a toy model where we know what should happen. There's lots more one can do quantitatively. And actually, since then, we've been developing tools where we actually do, not in the tree graph, but in simpler settings, really probe the spatial structure of entanglement. So I really think it's a first step to even start to connect. Part of it is even connecting two different communities, right? Figuring out a common language for even talking to theorists who think about gravity when all I know is quantum mechanics.
Well, I hope this is not a too sensitive question, but you mentioned Steve Gubser, who I didn't know. Was he alive to see the triumph of, his insight about how to do the setup, that it did really work?
He was not alive to see us do the experiment. Yeah. So we had a theoretical proposal published in Physical Review Letters, and it was really shortly after we wrapped that up that he tragically passed away in this climbing accident. I'm sad that he didn't get to see the experiment, and I still find it really motivating to try to kind of push forward and continue.
He clearly had some great insight because, as you say, it didn't seem obvious that that was the way to set things up.
Yeah.
Well, the whole thing really seems very high risk to me, I have to say. High risk, high reward. I'm just wondering, is that kind of who you are? Are you that type of scientist?
I'm somebody who looks for some of the problems I work on to be ones that everybody else isn't also working on. My sense is, if everybody else is already doing a thing, like I might not need to do it. And yeah, maybe that does draw me into things that are a little bit more on the risky side. And this direction of simulating quantum gravity is one that I find high risk, high reward. But that same toolbox has applications in enhanced precision measurements, in quantum computation. Even if it gives some new insight to the theorists that then take that to the next level to learn something about gravity in our universe, that would be amazing. If it even just gives us new ways of thinking about quantum mechanical systems, right, that can help us in that effort to engineer and understand quantum many-body systems, be it for applications in precision sensing, computation, understanding the design of materials, right? I think there's a broad effort to control and understand entanglement that will benefit from research in this area. And if it answers questions about gravity in our universe, that's amazing. But even if it doesn't, we won't have wasted our time.
I agree. It seems sort of surefire in a way. It can't possibly be as risky as it sounds because, as you say, how could it hurt to learn more about how to control quantum systems and manipulate them with entanglement? That has to be good.
That's what I think. Yeah.
Well, okay, so let me close with kind of an emotional question. What is it that really fires you up? What are you really trying to do? What's your motivation?
I really think that it does help get me motivated to know that something we learn in our experiments may have practical application, but it's not important to me personally that application is tomorrow. If it's 50 years down the line and actually it's not the application we thought it would be and it's a different one, that's fine with me. So I think I do believe deeply that fundamental science will ultimately have technological impact, but I enjoy it also just for the kind of thrill of being at the frontier of the unknown and trying to push that frontier forward.
Well, it's so exciting to hear about this. I really appreciate you taking the time to talk to us today, Monika, and thanks for being on The Joy of Why.
Thank you. It was a pleasure to chat.
I love this high-risk statement. I absolutely love that she said she likes to at least do some of her work in an area which is not crowded, that nobody else is working on. I love both those things. It really appeal to me. And I think it's where a lot of the great stuff happens.
But I wonder if your reaction is a little bit of a reflection of who you are.
Oh, absolutely.
I don't think this is for everybody.
It's not. It's not. And obviously, if you're going to build the James Webb Space Telescope, you don't want to be a high-risk thinker. I mean, it's a very risky project, right? But it was clear and well-defined. And the reason it was late and over budget is because they were minimizing the risk. Mm-hmm. So you definitely don't want everybody being like that. You want people to collaborate on big projects together and move in the same direction. But yeah, absolutely. Yeah. My whole life, people were telling me, don't work on that. Nobody's doing that.
Well, I think the secret is sort of like in relationships where You're looking for the match.
Yes.
And so I feel like there's a lot of ways to be a good scientist or mathematician, and you have to know yourself. So Monika clearly is not scared of risk. She's thinking about the long game. You know, she reminds me of Gaudi, that Sagrada Familia in Barcelona. You know, he didn't get to live to see it finished, but he had a great vision, and they're still building it as far as I can tell.
Yeah, an interminable project. Yeah.
But it's not for everyone. Not everyone has that kind of nerve. Like she could hit the jackpot, or she might, you know, get a nice little payout.
Mm-hmm. Yeah, it sounds like there's a lot of potential unanticipated consequences. I find that really inspiring. We throw something out in the world and we have to see who else is there to pick it up.
Well, it's always a pleasure to chat with you about these things.
And you, Steve.
Thanks, Janna. All right. Well, we'll see you next time.
We'll see you next time. Thanks for listening. If you're enjoying The Joy of Why and you're not already subscribed, hit the subscribe or follow button where you're listening. You can also leave a review for the show. It helps people find this podcast. Find articles, newsletters, videos, and more at quantamagazine.org.